All right, welcome everyone. For those of you that didn't attend a different section, you are welcome to watch this recording and fill out the attendance Google form that is also on the same page. Just make sure you fill out, you get your attendance. Today we'll be talking about Kepler's laws. I'll give you guys a few videos to watch about Newton's laws, and we'll go through a little bit of an activity. I am quite excited. This is a fun week. So first, we have our announcements. Your add drop deadline for this class is February 9th. Just remember, even though that the front of the class is very math and heavy loaded, we do get to some fun concepts later on. Your pass and fail switch deadline is April 1st. And I haven't stressed this before, but we do have an attendance policy for sections. You have to attend about 80% of sections in order to get your 100% participation in this. That gives you about 3 free absences. Yeah, I realize it's spelled wrong. But yeah, you have 3 free absences. You can use those at any time. If you do get sick with COVID, those don't count towards your free absences. Just let us know. We do have ways you can make up attendance. Usually it's just filling out the worksheet to your best of your ability. What else? Yeah, all right, so we're gonna go ahead and get started. So today we're going to start out with Kepler's laws. We're going to do a little bit of an activity. I would like you guys to follow along with this on your own sheet of paper. There's 2 ways you can do this. We can either just go the drawing route, or if you want to have a bit more fun, what you can do is get yourself a piece of cardboard, piece of paper, 2 push pins, and a string, and tie it in a circle. Put those circle around the pins and your pencil in that circle and draw it around and draw your own ellipse. Dr. Dressing talked about this activity in lecture. For our uses, we're just going to go ahead and start out drawing an ellipse. So if you go ahead and follow along, go ahead and to the best of your ability, draw an ellipse. It's not going to be perfect. It doesn't have to be, and that's totally okay. In this ellipse, draw 2 foci. If you're doing the push pin method, this would be where both of your push pins are. Take one of those and designate it as your sun. Fix this really quick. High names and indicators. Perfect. All right, then what I want you to do is also add a planet somewhere on your ellipse. Doesn't have to be really anywhere specific. You can name it whatever you want. I'm going to use Uranus just because I have a lot of fun with Uranus in my research. Next, I want you to take a point on the edge of your ellipse closest to the sun. This is your perihelion. And on the opposite side, near the other foci, this is your aphelion. Sorry if I botched the way you say it, but aphelion. And then go ahead and draw an X in the center of your ellipse, or as close to the center as you can get. If you take a dashed line from your aphelion to the X in your ellipse, label that A. This is your semi-major axis. It only goes through half of the ellipse. Next, I want you to, from the point of the sun, draw a bit of a triangle. It doesn't have to be perfect. It's going to be a smallish triangle. Label this as point D. This is point C. And on the opposite side, make a wider one. It's going to look something like this. This is point A. This is point B. If you remember in our discussion of Kepler's second law, the area of this triangle, which we'll label as A2, and the area of this triangle or cone is A1. They are equal to each other. Also, the time it takes to get from point D to point C and point A to point B are also equal to each other. So we're going to go ahead and this is the drawing you should have we're going to continue forward and we're going to do some questions based off of this. Oh, wrong way. All right, so this is about the drawing you should have and what it should look like. This is a GIF showing you about how the planet would go around an ellipse. The arrow you see is a vector of motion. A vector is something that has direction and magnitude. So as you notice on this end, it's going to have a smaller arrow than on this end. It's a lot larger, it's a lot faster. The gravity of the sun at this point in time has a lot larger effect on the planet than it does at this end. That's one of the reasons that we can get the change in speed. So now I have two questions for you. First, using your drawing of Kepler's laws, if A1 is equal to 3 times 10 to the 12th meters squared, what does A2 equal? So if you remember in your drawing, this is A2 and this is A1. I'll go ahead and pause and try to solve the question. All right, and if you remember, and we just mentioned A1 is equal to A2 in an ellipse. So A2 is equal to 3 times 10 to the 12th meters squared. All right. Ooh, too far. All right, and our next question is using the same drawing, if it takes 1 hour to get from point A to point B, how long does it take to get from point C to point D? Remember, this is C, D, A, and B. So it takes 1 hour to travel this far. How long does it take to travel this far? Go ahead and pause and answer the question. All right. And just like we also stated, the time it takes to get from point A to point B is equal to the time it takes to get from point C to point D. So the answer is 1 hour. All right. And now with Kepler's laws, I have them organized correctly. All right. I know we didn't go over them specifically in section, word for word on what they are, but I want you to use your own resources. Take your time, go ahead and write out what Kepler's 3 laws are in your own words. Yeah, the better you can write it on your own words, the more better you have the concept. So go ahead and try, pause and try. All right, so Newton's first law, or sorry, Kepler's first law, is that each planet moves around the sun in an orbit that is an ellipse, with the sun at one focus of the ellipse. We saw this in the way that we drew our ellipse, or in our activity. The second law is that straight line joining a planet and the sun sweeps out equal areas in the space in equal intervals of time. Now, in our specific drawing, we didn't connect it to a planet. We drew a planet in there, but this law still holds true. And our third law is the square of a planet's orbital period is directly proportional to the q of the semi-major axis of its orbit. So this comes out into the equation. This symbol that you see right here, this is a proportional system, meaning something is directly proportional. Typically, in this class, we'll write it as an equal sign. And this is an orbital period, and typically we'll display that in years. And this is the length of our semi-major axis. All right. Now I want you guys to attempt this problem. So Mercury has an orbital period of about 88 days. Using Kepler's third law, what is the semi-major axis of Mercury's orbit? AU is just our unit of our orbit. Go ahead and pause and figure it out. All right. You should have gotten, there we go, 0.4 AU, so B. So I'll walk you through how we did it. So first we have to take our 88 days and convert it into years. So times that, we know our conversions. There's 365 days in 1 year. Days cancels out, and this comes out to be 0.15 2, 4, 1. Now, we know that this is our equation, so we have to square this value. And that comes out to be 0.058. Now, in order to just get A, we have to take the cube root of each side. So A comes out to be 0.387, which rounds up AU, which rounds up to 0.4 AU. Now I want you to take a minute, go through these videos. You don't really have to do the first one if you don't want to. It's just a fun epic rap battle of history. If you didn't grow up with those, they are very fun videos to watch. I recommend going through them. But I'll also post the links in our page so they're easier to get to. The second one is more important for you to watch. This is a crash course on Newton's laws. They explain it very, very well, better than I could ever. So go ahead and watch that to about 6 minutes, and then we'll go ahead and continue on. All right, now after watching those videos and using any of the resources you have, I want you to take a chance and write out Newton's laws in your own words, the best you can. All right, go ahead and pause and do that. Then we'll go through them. So, Newton's first law is an object in motion or an object at rest will stay in motion or rest unless acted upon by an outside force. I don't know about you guys, but when I was a teenager, I was a very, very heavy sleeper. And the only time that my parents would get me to wake up is when they threw a whole bunch of cold water on me. It's one example. Or, a moving train will keep going at the same speed unless acted upon by an outside force. And typically with like friction, it'll start slowing down. You'll see this with your car too. If you just let your car drift, friction, air resistance will cause it to slow down. All right, a second law is the acceleration of an object produced by a net or a total applied force is directly related to the magnitude. We typically see this in force equals mass times acceleration. And lastly, we have Newton's third law, which is every reaction has an equal and opposite reaction. I always explain this. I don't recommend you doing it, but if you were to punch a wall with all your might, the wall is going to have the same amount of force applied back on your fist. It's going to hurt if you punched it with a lot of force. Punched it with a little, it's not going to hurt that much. This is how my physics professor explained it back in high school. It's my easiest way to relate it. All right, now what I want you to do is I want you to, using your resources, using your intuition, is figure out how Kepler's and Newton's laws intersect. And to your best ability, explain it to me. You can use equations, use your words, and then we'll go ahead and go through it. All right. So now that you have a chance to do that, here's a long-winded explanation that we're going to go through. Kepler's laws and Newton's laws, taken together, imply that a force that holds the planets in their orbits by continuously changing the planet's velocity so that it follows an elliptical path is 1, directed towards the sun from the planet, 2, is proportional to the product of masses for the sun and planet, and 3, is inversely proportional to the square of the planet-sun separation. This is precisely the form of the gravitational force with the universal gravitational constant G, which is listed in your worksheet as 6.67 times 10 to the negative 11th. Units are meters cubed per kilogram second squared, is our constant of proportionality for this. So our Newton's laws of motion with gravitational force used in the second law imply that Kepler's laws and the planets obey the same laws of motion as objects on the surface of the Earth. We see these in our two equations. We first can relate our orbital period, which if you remember from Kepler's third law, it now comes out to this equation. 4 pi squared, capital G, that's our gravitational constant, m1 plus m2 are two masses, and our semi-major axis comes into relation. And the second equation is our force of gravity is equal to our gravitational constant times two masses, or masses times each other, over the distance between them squared. You can use these with two giant blocks, like you would see in physics, or in the planetary sense between two massive planets. The one thing, though, is if, say, the mass of our first object is some giant planet, and it's significantly heavier than our second object, then basically in these equations, we're only going to take into account that first mass. The second mass is so light that it's negligent and doesn't actually affect our value that much. And this makes some math easier for the realm of astronomers. All right, so now I want you guys to try two more math problems for me. The first one is if m denotes a mass, so here we have m1, m2, m3, and d denotes our distance. So while I use d here in our equation, it's going to be r. The length of the distance, we show a value in meters. Which objects have a higher force of gravity between them? Objects m1 and m2, m1 and m3, or m2 and m3. So we want you to think in terms of Newton's universal law of gravitation, which is our equation 4 on page 2. I also put it here on the slide. Show your work and give your values for force in newtons, which is kilograms times meters per second squared. All right, I'm going to go ahead and pause and let you guys do that. Take as long as time as you need, and then we'll go through them. All right, welcome back. We're going to go ahead and go through the math of it. So we're going to have to do three different math problems. We're going to have to do the force between m1 and m2, the force between m2 and m3, and the force between m1 and m3. All right, so we're going to start with m1 to m2. We're going to be using the equation put up here. G is our gravitational constant, which is 6.67 times 10 to the negative 11th meters cubed per kilogram second squared, times our first mass is 5 kilograms. Our second mass is 3 kilograms. Divided by the distance between the two, which is 2 meters squared. This comes out to be 2.5 times 10 to the negative 10th newtons. Now, what's the most important thing here? If you said units, good on you. Units are very, very important. Luckily for us, all of our units cancel out into a point where we do get newtons. Sometimes when you're doing these kinds of math equations, you will end up with something with different units and you'll have to convert it. So just be careful on your way of doing so. All right, next, mass 2 to mass 3. Same equation, same setup. Gravitational constant times 10 to the negative 11th meters cubed per kilogram second squared, times, in this case, we're starting out with 3 kilograms. And our other one is 2 kilograms. And we divide that by the distance between them, which is 1 meter squared. And this one comes out to be 4 times 10 to the negative 10th newtons. Last but not least, the distance between m1 and m3. We have our gravitational constant once more. And this time we have 5 kilograms and 2 kilograms. And the distance between them is 3 meters. And this one comes out to be 7.41 times 10 to the negative 11th newtons. So our answer here is M2 and M3 is going to have the strongest force. So you can see that the distance between the two objects that we're measuring has a significant impact on the force between those two objects. One of the cool things to think about is with these laws, you have gravity. There is gravity between you and your laptop. There's gravity between you and the person sitting next to you. It's negligible to us, but it does exist. And you can use this in a lot of different senses. All right, I have one more question for you. All right, the next question I want you guys to work through is the gravitational acceleration at Earth's surface is 9.8 meters per second squared. If we doubled Earth's radius, what would the new gravitational acceleration be at Earth's surface? Go ahead and pause and try to figure it out. All right. And the answer you would come out to be 2.5 meters per second squared. So we can use these two equations here to do this relation. So we do mass times acceleration is equal to our gravitational constant, mass 1, mass 2, over r squared. Now we're going to be doubling this value, which means we have to square it. So basically, it's going to be 1/4 times this side. So as a result, we also have to multiply this side by 1/4. And if this formula ends up coming out to be 9.8 meters per second squared, then we can take that, multiply it by 1/4, and we get about 2.5 meters per second squared. All right. And that is everything I have for you guys today. Remember to fill out your attendance. Let me know if there's anything in these sections that you feel would be more beneficial. These sections are for your guys' benefit. So if you feel like we should be going through more homework, etc., let me know. I put a spot for it in the Google form. Go ahead and do that. I look forward to seeing you guys back in person. But remember, next week, we are also doing a recorded section. Yeah, I hope you guys have a great week. And thank you for stopping by.